Imagine a universe where the very first galaxies hold clues we're only just beginning to decode, and the most astonishing secret lies at the very bottom of our list. Stay tuned until number 1, because the final revelation could rewrite what we think we know about cosmic origins. Imagine spotting the faint glimmer of a star that may belong to the universe's very first generation. These elusive population 3 candidates shine with a pristine hydrogen-helium mix, lacking the heavier elements forged in later stellar generations. Astronomers hunt them in the most chemically primitive dwarf galaxies, where the interstellar medium has remained almost untouched since the cosmic dawn. Spectroscopic surveys reveal tiny traces of ionized helium that hint at these ancient powerhouses, though definitive confirmation still evades us. Their existence would illuminate how the first heavy elements were forged and dispersed, setting the stage for planet formation billions of years later. And coming up at number 9, a surprising chemical fingerprint that challenges our models.
Surprisingly, some primitive galaxies harbor pockets of carbon-rich gas that defy expectations of a metal-poor environment. While overall metallicities hover near 1/100th of the Sun's, localized regions show carbon abundances comparable to more mature systems. Researchers attribute this to the remnants of early supernovae that expelled freshly forged carbon into surrounding voids before the galaxy could fully enrich. These carbon-rich clumps act as cooling agents, enabling the formation of low-mass stars earlier than theory predicts. Their discovery forces a re-examination of how quickly the first elements spread across nascent galactic structures, suggesting a more chaotic and heterogeneous enrichment process than previously thought. Up next, a rare dark matter configuration that twists the shape of early galactic halos.
One of the most puzzling findings is the presence of dense dark matter cores in some of the smallest, oldest galaxies. Simulations traditionally predict a steep rise in density toward the center, but observations of dwarf spheroidals reveal a flatter, core-like profile. This discrepancy, known as the core cusp problem, hints that interactions between dark matter particles and baryonic feedback may have smoothed the inner halo even in galaxies with minimal star formation. If verified, such cores could provide the first empirical clues about the true nature of dark matter, perhaps pointing to self-interacting particles. The next secret, at rank 7, uncovers how gas streams silently feed these primitive systems.
Researchers have identified cold, pristine gas streams that quietly funnel into primitive galaxies, sustaining star formation long after the initial burst. These filaments, composed almost entirely of hydrogen and helium, thread through the cosmic web and deliver fresh fuel without adding significant metals. By tracing Lyman alpha absorption lines, astronomers map the velocity and temperature of these inflows, revealing that they can persist for billions of years, effectively delaying chemical enrichment. This steady supply helps explain why some early galaxies remain chemically primitive despite ongoing star formation. Coming up at number 6, we'll see how hidden magnetic fields influence the early galactic environment.
Hidden within the faint glow of primitive galaxies are magnetic fields that, despite their low strength, shape the motion of ionized gas. Recent radio observations using Faraday rotation measures suggest that even the earliest galaxies possessed coherent magnetic structures, likely amplified by turbulent dynamos during the first supernova explosions. These fields can channel gas flows, affect star-forming regions, and even influence the escape of ionizing photons that re-ionize the universe. Their subtle presence challenges the notion that magnetism only became significant in later, more massive systems. Next, at rank 5, we explore an odd abundance pattern that hints at exotic stellar deaths.
Rare isotopic signatures of nitrogen-13 have been detected in the spectra of some chemically primitive galaxies, an unexpected find given the short half-life of this isotope. Scientists propose that explosive nucleosynthesis in early, massive stars, perhaps parainstability supernovae, could have briefly flooded their surroundings with this rare form before it decayed. The fleeting nature of nitrogen-13 means we're catching a snapshot of a very specific epoch, offering a unique window into the death throes of the first stellar giants. This discovery not only refines our models of early stellar evolution, but also underscores how even fleeting isotopes can leave lasting imprints on galactic chemistry. Up next, an unexpected alignment of satellite galaxies that reshapes our view of early clustering.
Unexpectedly, several primitive galaxies exhibit a planar alignment of their tiny satellite companions, forming thin, co-rotating disks rather than random halos. This arrangement mirrors the so-called satellite plane observed around the Milky Way, but its presence in early, Low-mass systems suggests that such structures may arise naturally during the initial stages of hierarchical assembly. Simulations indicate that filamentary accretion along the cosmic web can imprint these planar configurations early on, before major mergers scramble them. If these alignments are common, they could provide a fossil record of the large-scale structure that seeded galaxy formation. Coming up at rank 3, we delve into ancient star clusters that survived the tumultuous early universe.
Ancient globular clusters, some older than 13 billion years, have been found embedded within the most chemically primitive galaxies, acting as living relics of the universe's first star-forming episodes. Their tightly bound stellar populations exhibit extremely low metallicities, indicating formation before significant chemical enrichment took hold. Detailed color magnitude diagrams reveal multiple stellar generations, suggesting that even these early clusters underwent complex internal evolution. Their survival through billions of years of tidal interactions offers clues about the gravitational stability of early galactic potentials, and the role such clusters played in seeding later star formation. Next, at number 2, we uncover a striking discrepancy in the galaxy's rotation curves.
Striking rotation curve anomalies have been observed in several primitive dwarf galaxies, where the outer gas rotates faster than expected from their visible mass alone. While this phenomenon is often attributed to dark matter, the magnitude of the discrepancy in these low-mass systems is larger than standard cold dark matter models predict. Some researchers suggest that alternative gravity theories or self-interacting dark matter could better explain the steep rise. Others point to past merger events that might have redistributed mass in unexpected ways. This ongoing debate highlights how the simplest galaxies can become the toughest testing grounds for fundamental physics. Finally, at number 1, we reveal the ultimate secret that could redefine our understanding of cosmic beginnings.
Finally, the ultimate secret lies in a faint, global 21 cm absorption signal that appears to be imprinted by the earliest primitive galaxies during the cosmic dawn. Detected by radio experiments targeting the sky-average spectrum, this dip suggests that the first galaxies cooled the surrounding hydrogen gas more efficiently than standard models anticipate, possibly due to exotic interactions between dark matter and baryons. If confirmed, the signal would provide a direct, time-resolved glimpse into the era when the first luminous sources ignited, marking the transition from the dark ages to a universe filled with light. This revelation not only reshapes our timeline of galaxy formation, but also opens a new frontier for probing the fundamental properties of dark matter itself.
We've journeyed through the faint whispers of ancient stars, the puzzling metal-poor clouds, and the invisible scaffolding of dark matter that shaped the earliest galactic neighborhoods. Each secret not only deepens our wonder but also sharpens the questions that drive modern astronomy forward. If you enjoyed uncovering these hidden facets of the early cosmos, subscribe so you won't miss the next mind-blowing list we release each week. Which of these 10 secrets surprised you most? Share your thoughts below, and if you found this countdown enlightening, give it a like to help the channel grow.